Hey everybody, so I'm going to run through some chapter 1 and 2 slides actually. Um, so let's get to it. Combination of material here. Chapter 1 doesn't get into too much of the physics, but it touches on it, so I combined some more. Chapter 2, motion in one dimension. We're talking about describing motion, describe and analyze linear motion. Different types of motion diagrams, different ways to represent motion. These are pictures, and assume that there is a photograph being taken every certain amount of time, so every 1 second, let's say. So you can determine what type of motion an object is undergoing from these types of diagrams. All right. So motion diagrams are made of two cars, right? Both have the same time interval between photos. Let's just say 1 second. Which car, A or B, is going slower? All right, so you want to see which car is traveling the least amount of distance between each photograph, right? And so, of course, that would be car A, right? Every second, there's a picture being taken, and the car has not gone that far, whereas car B, the yellow car, much greater distance in between each successive photo. All right, so car A. Here's something we call a dot diagram, just another way to kind of do the same thing. Two runners jog along a track. The positions are shown at 1 second intervals. Which runner is moving faster? And of course, really the only difference here is that you have this kind of on a number line. And so X just represents the fact that it's a horizontal number line, and M is meters, right? So a unit, so 0 to 50 meters. And now we're assuming there's no time listed, but it says not on the diagram, but it says they're at 1 second intervals. So which runner is moving faster? Well, it should be the one that is has more space in between each dot, right? So of course that would be A. Okay. Another one, we're going to talk about this in a little bit, but another type of motion diagram, bicycle moving to the left with increasing speed. Which of the following motion diagrams illustrates this motion? Well, these are just arrows, but you've probably seen these before. We call these vectors, and they can represent, in this case, speed, or I should say, to be more specific, velocity. I'll get into that a little later. But they give the direction of motion as well as how fast it's going based on the length. So these can be a good way to describe motion as well. So since that's the case, we have the arrows need to be pointing to the left, and if a longer arrow means a faster speed, they should be getting longer. So if that's the case, where are we going? Oh, if that's the case, then we're looking at B. So B right there. That's moving to the left with increasing speed. All right. To specify a position, we need a reference point. Okay, so this is very simple. We're going back to real straightforward mathematics here. We have number lines. Counting on a number line. You might not remember the last time you were counting on a number line, but this is kind of the foundation of some more complex problems. So we have a number line. We have our spot at 0 here, and positive distance this way, negative distance, or I should say displacement this way. We have the post office in the middle, the car at 4 miles to the right, and the cow at 5 miles to the left. All right. So having this set up with a number line gives you the opportunity to have a distance and a direction, both from the origin. So it gives you a little more information, and that's a beneficial thing. So the combination of an origin and axis marked in both the positive and negative direction gives us a coordinate system. And so you can probably imagine where we're headed. We're going to have a coordinate system, x and y plane, and things of that nature. We will be getting into that soon. So x-axis, horizontal motion, motion on a ramp. We'll talk about that a little bit. And generally, this is how it works. We have positive x, just like on a standard coordinate system that you might do in math, right? That positive is to the right, negative numbers are to the left, and then we have positive y values, anything above that origin of 0, and then negative y values down to the bottom. So having this established allows us to give a direction to any number that we have. The numbers we usually call magnitudes, and then we have directions. So we'll talk about that a little bit more. This is a standard setup. We will come across problems where you can establish the coordinate system yourself. If you want to completely flip this, you're welcome to do that. Make positive x, or I should say, to the right in the horizontal direction negative, and to the left in the horizontal direction positive, and vice versa with the y. Up in the y direction is negative, down is positive. Some problems will make sense to do it this way. It will just depend on the scenario. But this is the standard, and most of the time we will use this. Change of position is called displacement. So final position is over here, this spot right there, and the initial position right here. And now I actually realize this whole thing is wrong down here, so I want to make sure you are aware of that. This is not correct. Let's get that out of there. Displacement, the definition of displacement, the difference between the final position and the initial position. All right, you get a change in something. The change is always the final minus the initial. All right, that is pretty standard. So what this would be, let's see if I can find this. Here we go. So we have the change in position, the final position, which is 0. Right? Oh, it's feet, huh? All right. Hold on. Let me see if I can do this. Pointer. There we go. All right. And pen. All right. So it's 0 feet minus the initial position, which is 50 feet. And that equals, of course, negative 50 feet. So the displacement of this car, or this person, we'll say it's a person walking down 12th Street, is negative 50 feet based on this coordinate system. Now, you could have a different coordinate system, and then your displacement would be a little different. But based on this coordinate system, the displacement of this person walking down 12th Street is negative 50 feet. The negative sign, all right, negative signs in physics just tell you direction. So since to the right is positive and to the left is negative, that just means this person walked 50 feet to the left. That is what that means. All right, representing position. All right, so here we have these vectors. All right, so we have a section in time starting at 0 minutes, and during the first section here, 1 frame per minute. So the first 3 minutes, this person walks a certain distance, right? During the next 3 minutes, they walk another distance, and that distance is much less. Where are we here? Oh, here's the second 3 minutes, and then in the final 3 minutes, they walk this very large distance. So what can we say about this speed? Well, in the beginning, they're walking a certain speed, and then they slow down, right? In the second 3 minutes, they don't move as far, and the final 3 minutes, they move a lot. All right, so every dot represents the student's position. And then this graph down here, we've plotted each point on a position versus time graph. All right, and so one thing you can look at here is that the when we're looking at each section, right, that's kind of like broken up into 3 sections here. All right, so I'm going to label these A, B, and C. We already talked about how fast each one was going. B was the slowest, C was the fastest, and A was somewhere in the middle. So what we can see is if we take a slope of just section A, looks something like that. And then if we take the slope of just section B, it looks something like that. And then if we take the slope of just section B, or C, I'm sorry, it looks something like that. What do we notice? Well, the flattest slope is B, the steepest slope is C, and then somewhere in the middle is A. So what does that mean? Well, that means that the slope is equal to the speed at which something is moving. So a slope of position versus time equals the velocity. Okay? We'll talk about this a little more as we get going, but this is a very important concept going forward. And just on your own, take a look at the units of the slope, right? Rise over run, change in y divided by change in x. And you'll see that it matches. All right. I'm going to let you pause this, take a look at this problem in the effort of time here, and figure out an answer. Have the answer on the next, no, don't have the answer on the next page, but take a look at that last one and see if you can get an answer. It's real straightforward. Motion at a constant speed is called uniform motion. So it's moving at a constant speed, basically. There's the equation for it, distance traveled during a time interval divided by that time interval. That is speed. Doesn't matter the direction. Speed only measures how fast you're moving. That's important. But velocity tells you both its speed and the direction that it's going. So we talked about displacement, how far you are from a starting point or a reference point or an origin. Distance, if we go back, distance is just how far you go, right? So you might start at 0, go all the way to 60, go back to 40, go out to 100, go back to 60, go out to 120. The displacement would be, if you started at 0 and ended at 120, the displacement is 120. But the distance is all of those individual legs added up together. Doesn't matter the direction that you go. All right, so displacement divided by time, that is velocity. Gives you more information because it's how fast and in what direction. Okay? All right. Speed of an albatross. Pause this, practice this, take a look. Answers on the next one. Let me move this down so you can see. There you go. Move on. Here's another example. At 12 seconds, Frank is at 25 meters. 5 seconds later, he's at 20 meters. What is Frank's velocity? Let's move that up. So this example gives you velocities to the left are negative, and that 12 seconds doesn't mean anything. So this would be change in position equals, we only have a few seconds here, final minus initial. All right, divided by, and then this whole thing divided by time, divided by So that is velocity, and that's how we get it. All right, I'll stop there.